Hello, my name is Robert Smith, and I'm with New River Community College. And today we are looking at the effect of pH on the solubility of species. Specifically, we're looking at how much of a given, in this case, ammonia, is needed to precipitate iron 2 hydroxide from a 0.0060 molar solution of iron 2 chloride. So the main thing that we're looking at here is how does the pH, in this case, we're worried about the hydroxide ion, so the POH influence precipitation. So let's have a look. We'll need to write down three equations, three chemical equations. The first being that we know that iron 2 chloride, FeCl2, is going to dissolve into iron 2 plus 2Cl minus. So we know that the concentration of iron 2 plus is equal to 0.0060 molar. Okay, that's the first thing, first little bit of information. The next two are, we want to look at ammonia. So NH3 plus H2O is going to give us ammonium ion plus hydroxide. And similarly, we can think about free floating iron plus the hydroxide forming iron 2 hydroxide, which will precipitate out as a solid. So we'll write it like this: Fe2 plus 2OH minus gives us FeOH2. And that'll be a solid. So we're trying to get some solid. We want to see what is the minimum amount of ammonia that we need to add to the solution of iron 2 chloride in order to make iron 2 hydroxide crash out of solution. We don't want to necessarily get the maximum amount. We just want to know how much, like the very bare minimum of ammonia that we need in order to start that process. So we'll start with writing a solubility product equation. So KSP is our solubility product, and it's going to be, typically it's products over reactants. So I wrote this in the reverse order, but so the main thing with solubility product is you're just multiplying your species, your ionic species. So Fe2 plus times OH minus raised to the power of its coefficient. So that's 2. So that's the solubility product equation for iron 2 hydroxide. And then what we'll need to do is we'll need to look up the KSP, which I've already done. KSP for iron 2 hydroxide is 1.6 times 10 to the minus 14. With that, we now know what the concentration of iron is from up here, and we know what the solubility product, so we can rearrange our formula by dividing by iron, the concentration of iron to both sides. So we have OH minus squared is equal to 1.6 times 10 to the minus 14 over 0.0060, which when you do that calculation, it ends up giving you 2.7 times 10 to the minus 12 molar squared. So next what we'll need to do is we'll take the square root of both sides, and we find that the concentration of hydroxide is 1.6 times 10 to the minus 6. Okay, so now that we have the concentration of hydroxide, we'll have to set up an ice table using this equation here. So let's do that. So I'm going to exclude water because it will not be influenced in the ice table, but recognize that it's there. So we have NH4 plus OH minus. So you can see how the water would come out of that equation. And then ICE. So unlike most of the ice problems that we've done in the past, this one, we don't know what the initial concentration of ammonia is. But we do know that the other two are 0. And we know that the change in ammonia will be minus 1.6 times 10 to the minus 6, because that is the concentration of the hydroxide. So that one has to end up 1.6 times 10 to the minus 6. So similarly, our ammonium ion will have to have 1.6 times 10 to the minus 6. And that means that our concentration of ammonia at equilibrium is X minus 1.6 times 10 to the minus 6. And then you simply set up your look up your Kb, because we're dealing with a base, and set up your equilibrium equation. So it would be Kb is equal to products over reactants. So Kb in this case is 1.8 times 10 to the minus 5. Products are 1.6 times 10 to the minus 6 times 1.6 times 10 to the minus 6. And that's why I didn't take the square root initially, because we can just pull that off this number right here. So it's 2.7 times 10 to the minus 12 over X minus 1.6 times 10 to the minus 6. Okay. So from there, you would multiply both sides by X minus 1.6 times 10 to the minus 6. And you would isolate X by, you would distribute 1.8 times 10 to the minus 5 to X and negative 1.6 times 10 to the minus 6. And that would be equal to 2.7 times 10 to the minus 12. Once you've done all this and you've gotten X on one side, you should end up with 1.8 times 10 to the minus 5x is equal to 3.2 times 10 to the minus 11. So then X would equal 1.8 times 10 to the minus 6 molar, which is also equal to the concentration of ammonia. So in order to get, you have a solution of iron 2 chloride and you have some ammonia. In order to get some iron 2 hydroxide out of solution, you have to put in at least 1.8 times 10 to the minus 6 molar. You have to add ammonia till you reach that concentration in order to get your iron 2 hydroxide to crash out.